In September 2020, a team of astronomers studying the atmosphere of Venus published a paper that immediately unsettled the scientific community. They had detected phosphine. On Earth, phosphine is associated almost entirely with biological activity, and they were detecting it in the cloud layers of a planet hot enough to melt lead. The signal was controversial. Some scientists challenged it, others defended it, but the larger problem never went away, because Venus is only one of several places in our solar system where the evidence has started becoming difficult to ignore. Right now, a moon orbiting Saturn is ejecting enormous plumes of water vapor, salt, hydrogen, and organic molecules hundreds of kilometers into space. Beneath the frozen crust of Jupiter's moon Europa sits a liquid ocean containing more water than all of Earth's oceans combined. On Mars, NASA's Curiosity rover detected methane spikes that appear and disappear faster than known atmospheric chemistry should allow. And Titan, Saturn's largest moon, contains rivers, lakes, rain, and weather systems built not from water, but from liquid methane and ethane. For decades, the search for life beyond Earth belonged mostly to speculation. Now it belongs to planetary science. We make these long form space documentaries because we love this stuff, and so do you. If you want to keep exploring with us, subscribe and we'll be here whenever you need a quiet journey through the cosmos. It starts with the three conditions NASA believes every living system in the universe may require. A biosignature is any signal produced by life that resists easy non living explanation. Sometimes it appears as a gas suspended inside an atmosphere. Sometimes it survives as unusual chemistry trapped in ancient rock. Sometimes it emerges as molecules behaving in patterns that should collapse quickly unless something continues replenishing them. When NASA searches for life beyond Earth, this is what its instruments are designed to detect. Not cities, not spacecraft, evidence. Astrobiologists reduce the problem to three requirements considered essential for life as we currently understand it: liquid water, a source of energy; organic chemistry, meaning carbon based molecules capable of building complex biological structures. Wherever these three conditions overlap on Earth, life pushes into the environment with astonishing persistence. Beneath Antarctic ice, inside acidic lakes, around volcanic vents buried kilometers below the ocean's surface. Life does not seem fragile once it begins. It spreads, but distance shapes the search itself. Thousands of exoplanets orbiting distant stars have now been confirmed. Some are rocky worlds positioned within temperatures suitable for liquid water. A few may even possess atmospheres vaguely resembling Earth's, yet almost all remain tiny shadows crossing distant starlight. We observe them indirectly, measuring faint chemical fingerprints from unimaginable distances. The solar system allows something radically different. Here we can physically investigate. We can lower rovers into dried riverbeds on Mars. We can send orbiters through plumes erupting from hidden oceans. We can deploy landers, spectrometers, drills, and eventually return samples directly to Earth laboratories. The search stops being purely observational. It becomes tactile, measured grain by grain. For much of the 20th century, scientists believed habitable worlds could only exist inside the habitable zone, the narrow region around a star where surface temperatures permit liquid water. Earth sits comfortably within this band. Venus lies too close to the Sun. Mars drifts near the frozen edge. Then the outer moons changed the equation completely. Tidal heating shattered the old model. The mechanism is deceptively simple. A massive planet continuously stretches and compresses a nearby moon through gravity alone. That repeated flexing generates internal friction. Friction creates heat. Deep beneath frozen surfaces, entire oceans can remain liquid despite existing billions of kilometers from the Sun. Europa experiences this around Jupiter. Enceladus experiences it around Saturn. Beneath their ice shells, water persists in darkness under enormous pressure. One discovery transformed the number of potentially habitable environments in our solar system from a single confirmed world to at least six major candidates, and none of this belongs to speculative science. Everything we discuss comes from peer reviewed research, spacecraft telemetry, spectroscopy, radar mapping, geological analysis, or statements issued directly through NASA's astrobiology program. As of 2024, NASA spends more than $100 million annually on astrobiology research alone. Institutions do not sustain that scale of investment for distant fantasies. They sustain it when the evidence keeps accumulating. Jupiter pulls on Europa constantly. Every 3.5 days, the small moon completes another orbit through one of the harshest gravitational environments in the solar system. Nothing about its surface suggests habitability. Europa is slightly smaller than Earth's moon, covered in fractured ice and locked beneath temperatures near minus 160 degrees Celsius. Exposed skin would freeze almost instantly there. Metal would become brittle. Breath itself would crystallize. And yet the ice is not stable. Beneath that frozen crust lies a global ocean unlike anything once imagined possible so far from the sun. Current estimates place the ice shell between 15 and 25 kilometers thick. Underneath it, liquid water may extend downward another 60 to 150 kilometers into darkness. The scale becomes difficult to picture. Earth's deepest known point, the Mariana Trench in the Pacific Ocean, reaches roughly 11 kilometers. Europa's ocean could be more than 13 times deeper. But the most extraordinary detail is not the water itself, it is the heat. Europa should have frozen solid billions of years ago. Sunlight at Jupiter's distance is weak, only about 4% as intense as what reaches Earth. Yet Jupiter's gravity bends Europa continuously as the moon travels along its slightly elliptical orbit. The interior flexes over and over again. Rock shifts, ice strains, friction accumulates, heat builds slowly from within, the same way a repeatedly bent metal rod begins warming in your hands. That process is called tidal heating. Without it, Europa would likely be a silent sphere of ice. With it, an entire ocean remains alive beneath the surface. In 2012, the Hubble Space Telescope captured evidence that something beneath the crust was escaping into space. Faint plumes of water vapor erupted from Europa's southern hemisphere, rising hundreds of kilometers above the moon before dispersing into Jupiter's radiation environment. Material from the hidden ocean may already be venting outward naturally, carrying traces of the chemistry below directly into space where spacecraft can eventually sample it. Older evidence had already pointed toward the same conclusion. When NASA's Galileo spacecraft orbited Jupiter during the 1990s, its instruments detected strange magnetic fluctuations surrounding Europa. The moon's magnetic behavior changed in synchrony with Jupiter itself. Scientists eventually reached one dominant explanation. Beneath the surface existed a conductive layer interacting with Jupiter's magnetic field. Salt water conducts electricity extremely well, which means Europa's ocean is probably salty. Salt matters because it suggests prolonged contact between liquid water and rocky minerals below the seafloor. Water interacting with rock releases chemicals and energy gradients capable of driving complex reactions. On Earth, these environments often form hydrothermal vents, fissures where superheated mineral rich water rises through the ocean floor. No sunlight reaches those ecosystems, yet life thrives there anyway, sustained entirely by chemistry rising from the planet beneath. The Pacific Ocean floor was supposed to be barren. When the research submersible Alvin descended into the Galapagos Rift in 1977, biologists expected silence below. At roughly 2,500 meters depth, sunlight vanishes completely. Photosynthesis becomes impossible. No green plants survive there. No algae drift through the water column. By every traditional biological assumption of the time, complex ecosystems should not have existed, but Alvin's lights revealed movement. Clusters of enormous tube worms surrounded towering hydrothermal vents rising from the seafloor like underwater chimneys. Some stretched over 2 meters long, their pale bodies swaying slowly in superheated currents. White crabs crawled across mineral deposits. Dense mats of bacteria coated the rocks in shimmering layers. The water itself looked strange, dark with dissolved minerals erupting upward from inside Earth's crust. Nothing there depended on sunlight. The vents released hydrogen sulfide, methane, iron, and other chemicals from deep beneath the seafloor. Microorganisms consume those compounds directly through a process called chemosynthesis, meaning the conversion of chemical energy into biological energy. Instead of harvesting light like plants on Earth's surface, these microbes metabolized inorganic molecules from the vents themselves. Life had discovered another pathway. The discovery altered biology permanently because it severed one of humanity's oldest assumptions. For centuries, the sun had been considered the foundation of every ecosystem on Earth. Even predators in the deepest oceans ultimately depended on surface photosynthesis somewhere above. But the Galapagos Rift ecosystems operated independently from sunlight entirely. They were powered by geology that mattered immediately for Europa. If life on Earth could survive around hydrothermal systems in perpetual darkness, then oceans hidden beneath ice no longer seemed automatically sterile. The comparison was impossible to ignore. Europa possesses liquid water. Europa likely contains a rocky seafloor. Europa experiences internal heating generated through gravitational flexing. The same ingredients appearing around Earth's vents seemed increasingly plausible there as well, but the parallels kept growing stronger. Over the decades following Alvin's descent, scientists discovered hydrothermal ecosystems across multiple ocean basins on Earth. More than 500 unique species have now been documented around vent environments, many existing nowhere else on the planet. Some bacteria thrive in temperatures above 100 degrees Celsius under extreme pressure. Giant clams survive by hosting symbiotic microbes inside their own tissues. Entire food chains emerge without any dependence on sunlight from above. At NASA's Jet Propulsion Laboratory in California, researchers began studying these vent systems as direct analogs for extraterrestrial oceans. An analog means an Earth environment used to model conditions somewhere else. Instruments intended for icy moons are routinely tested in deep ocean environments because the physics, chemistry, pressure, and darkness overlap in meaningful ways. And slowly the scientific conversation shifted. The question stopped being whether oceans like Europa's could theoretically support life. The chemistry appears capable. The energy sources appear present. Water persists in enormous volume beneath stable ice for immense spans of time. The harder question became far more profound. Given enough time and enough chemistry, does life eventually begin wherever conditions allow it? Before dawn on October 14th, 2024, floodlights illuminated Launch Complex 39B at Kennedy Space Center in Florida. Moisture drifted through the night air. Beneath the tower stood a Falcon Heavy rocket carrying the most ambitious robotic investigation of an ocean world ever attempted. Europa Clipper left Earth at precisely 12:06 p.m. Eastern Time. For decades, Europa existed mostly as inference and probability, a hidden ocean deduced through magnetism, gravity, and fractured ice. But this mission was built to move beyond indirect evidence. NASA designed Europa Clipper to examine habitability directly, not from a distant telescope, but from inside Jupiter's system itself. The spacecraft is enormous, with its solar arrays fully extended. Europa Clipper spans more than 30 meters across, making it the largest spacecraft NASA has ever constructed for a planetary science mission. Jupiter receives only about 1/25 the sunlight Earth does, so the vehicle requires vast solar panels simply to remain operational in deep space. But Europa Clipper will never land. Jupiter surrounds Europa with lethal radiation, intense enough to damage electronics rapidly during prolonged exposure. Instead of entering permanent orbit around the Moon, the spacecraft will perform 49 close flybys between 2030 and 2034. Some passes will skim within 25 kilometers of the surface, briefly diving through the radiation before retreating outward again. Each pass gathers another layer of evidence. One of the mission's most important instruments is MASSPEX, short for mass spectrometer, for planetary exploration. A mass spectrometer identifies molecules by measuring their mass and electrical charge. As Europa Clipper flies through water vapor erupting from the Moon, MASSPEX will sample the plume directly, molecule by molecule. If amino acids exist there, it can detect them. If complex lipids, carbon chains, or unusual organic compounds drift upward from the ocean below, the instrument is sensitive enough to identify traces at extremely low concentrations. Not proof of life, but potentially the chemistry associated with it. Another instrument peers downward instead of outward. Reason, meaning radar for Europa assessment and sounding, ocean to near surface, will transmit radar waves through Europa's crust to map the internal structure beneath the ice. Radar works by bouncing radio waves off hidden layers and measuring the returning signal. Scientists hope Reason will identify buried lakes, thinner ice regions, and pathways connecting the deep ocean to the surface. The spacecraft also carries a surface dustinizer capable of capturing microscopic particles blasted upward from Europa's terrain. Tiny grains of ice and mineral dust may preserve chemical information from below, frozen inside them for thousands of years before escaping into space. NASA has stated the mission objective clearly. Europa Clipper exists to determine whether Europa possesses conditions suitable for life. Every trajectory, instrument, and measurement revolves around that question. The mission cost has reached roughly $5 billion, making it the most expensive planetary science program in NASA history. And now it is already moving outward through the dark between planets, on course to arrive at Jupiter in April of 2030. Saturn's E-ring is constantly being rebuilt. The ring appears diffuse and ghost-like from a distance, stretching hundreds of thousands of kilometers through Saturn's system in a faint halo of ice particles. For years, astronomers debated where that material originated. Rings slowly disperse over time. Something had to be replenishing it continuously. Then Cassini found the source. In 2005, while passing near Saturn's moon Enceladus, the spacecraft photographed towering jets erupting from the moon's southern hemisphere. Bright streams of water vapor and ice particles burst outward through long fractures in the ice, escaping directly into space. Enceladus itself is small, only about 504 kilometers wide, compact enough to fit comfortably within the borders of France. Yet, this tiny moon was behaving like an active world. The fractures became known as tiger stripes. There are four primary fissures near the South Pole, each roughly 130 kilometers long and about 2 kilometers wide. Infrared observations revealed something even stranger. The surrounding terrain remained intensely cold, but the tiger stripes were dramatically warmer by nearly 200 degrees Celsius compared with nearby regions. Heat was escaping from below, and the plumes never truly stopped. Some rose nearly 800 kilometers above the surface before dispersing into Saturn's E ring, feeding the structure continuously with fresh material. Cassini eventually flew through those plumes 23 separate times across its 13-year mission, sampling them directly using onboard instruments. The results transformed Enceladus almost overnight. Cassini detected water vapor first, then sodium chloride, ordinary table salt. Silica nanoparticles followed, microscopic grains usually associated on Earth with interactions between hot water and rock deep beneath the seafloor. Carbon dioxide appeared in the samples, so did methane, then molecular hydrogen. That last discovery mattered profoundly. Molecular hydrogen consists of two hydrogen atoms bonded together. On Earth, it commonly forms near hydrothermal vents through a process called serpentinization, where seawater reacts chemically with hot mineral-rich rock. Microorganisms at deep ocean vents use that hydrogen as an energy source, metabolizing it in complete darkness. Enceladus appeared to possess the same chemistry. But Cassini kept finding more. Complex organic molecules drifted through the plumes as well, including propane, butane, and acetylene, carbon-rich compounds capable of participating in increasingly sophisticated chemical reactions. The moon was not merely ejecting water. It was ejecting ingredients associated with habitability itself. Then came phosphorus. In 2023, a reanalysis of Cassini data published in Nature Astronomy identified phosphorus compounds within the plume material. Phosphorus is essential to every known form of life on Earth. DNA depends on it. RNA depends on it. Cell membranes require it. Energy transfer inside living cells uses phosphate molecules constantly. Before that discovery, phosphorus had never been confirmed in an extraterrestrial ocean. Frank Postberg of Freie Universität Berlin, lead author of the study, stated that Enceladus now appears to satisfy every currently known requirement for habitability. Water exists there. Organic chemistry exists there. Internal energy exists there. And, unlike many worlds in the solar system, Enceladus is not hiding those conditions from us. It is throwing them directly into space. At 11:55 a.m. Eastern Time on September 15, 2017, a faint radio signal reached Earth from nearly 1.5 billion kilometers away. Then the signal stopped permanently. Cassini had entered Saturn's atmosphere, traveling at roughly 111,000 kilometers per hour. The spacecraft began tearing apart under extreme heat and pressure high above the cloud tops. Its antenna remained pointed toward Earth as long as possible, transmitting data continuously until atmospheric friction overwhelmed the systems one by one. NASA destroyed it intentionally. The spacecraft still functioned, its instruments still worked, but engineers understood that Cassini was slowly running out of fuel after 13 years operating inside Saturn's system. Without precise control, the spacecraft might eventually crash accidentally into Enceladus or Titan, moons now considered plausible habitats for extraterrestrial life. Even microscopic Earth contamination carried aboard the probe represented an unacceptable risk. So, a $3.26 billion spacecraft was sacrificed deliberately. That decision revealed something profound about how seriously these worlds are now treated within planetary science. By the end of Cassini's mission, Enceladus was no longer viewed as an inert, icy moon. It had become a protected environment, and Cassini earned that transformation. The spacecraft launched in October of 1997 aboard a Titan IV rocket and arrived at Saturn in July of 2004 after a 7-year journey through the solar system. Over the next 13 years, it completed 293 orbits of Saturn and conducted 127 targeted flybys of its moons, building the most detailed portrait of the Saturnian system ever assembled. Enceladus emerged as one of the mission's greatest revelations. Data from Cassini confirmed that the moon contains a global subsurface ocean rather than a small, isolated reservoir. Measurements of the moon's wobble, called libration, revealed that the ice shell floats independently above a planet-wide body of liquid water. More importantly, the ocean appears to rest directly against a rocky seafloor below. That interface matters enormously. When liquid water contacts warm mineral-rich rock, chemistry intensifies. Reactions produce energy gradients, dissolved compounds, and potentially hydrothermal systems capable of supporting microbial ecosystems. Cassini detected evidence that exactly this process is occurring on Enceladus today. Tiny silica nanoparticles drifting through the plumes pointed toward active hydrothermal vents deep below the ice. The particles form most efficiently in hot water, interacting with rock at temperatures near 90 degrees Celsius. This became the first confirmed detection of active hydrothermal activity anywhere beyond Earth. But the chemistry grew even more intriguing. Cassini's instruments identified large carbon-rich organic molecules within the plume material, some exceeding 200 atomic mass units in size. Atomic mass units measure molecular weight at the atomic scale. These were not simple gases or isolated compounds. They resembled complex fragments associated with advanced organic chemistry, possibly produced through prolonged chemical processing in the hidden ocean below. The mission reshaped Saturn itself as well. By the time Cassini ended, evidence suggested at least 7 Saturnian moons possess subsurface liquid water in some form. Ocean worlds were no longer rare exceptions in the outer solar system. They were becoming increasingly difficult to avoid. Some spacecraft search for environments that might support life. Enceladus Orbelander is being conceived for something far more direct. After Cassini transformed Enceladus from an obscure icy moon into one of the leading astrobiological targets in the solar system, researchers began designing a mission specifically around biological detection itself. The proposal was submitted to NASA's Planetary Science Decadal Survey, the influential review process that establishes scientific priorities for the following decade of exploration. The mission concept carries an unusually explicit name. Enceladus Orbelander would combine 2 spacecraft architectures into one system. It would first operate as an orbiter, circling the moon repeatedly while flying through the active plumes erupting above the South Pole. Then it would descend and become a stationary lander near the tiger stripe fractures themselves. The mission profile unfolds slowly. For roughly 1.5 years, the spacecraft would remain in orbit around Enceladus, conducting plume fly-throughs and remote sensing observations. Remote sensing means analyzing a world from a distance using cameras, spectrometers, thermal instruments, and radar rather than direct surface contact. During this orbital phase, the spacecraft would repeatedly sample fresh material escaping from the interior ocean into space. Then it would land. The proposed landing site lies close to the south polar terrain where heat escapes through the fractured ice crust. There, the spacecraft would remain operational for approximately 2 years, conducting in situ analysis, meaning direct examination within the local environment itself rather than relying on orbital measurements alone. But the most extraordinary aspect of Orbelander is not where it goes, it is what it carries. Previous planetary missions were generally designed to assess habitability, searching for water, chemistry, temperature ranges, and geological conditions favorable to life. Enceladus Orbelander would move beyond that threshold entirely. Its instruments are being conceptualized to search for life directly, not indirectly, directly. Proposed payloads include instruments capable of identifying individual microbial cells, cell membranes, complex organic structures, and even genetic material if anything resembling terrestrial biology exists within the plume particles. No spacecraft in history has ever been designed with that level of biological specificity as its primary objective. One instrument concept resembles an entire laboratory compressed onto a tiny chip. The system uses microfluidics, the controlled manipulation of microscopic liquid volumes through miniature channels smaller than a human hair. Inside this microfluidic laboratory, captured plume samples could be chemically processed, isolated, cultured, and examined under magnification. If microorganisms exist within the ocean and survive transport through the plumes, the spacecraft may be capable of observing them directly. That possibility changed how the mission was ranked. The Decadal Survey identified Enceladus as one of the highest priority destinations for future exploration, second only to Uranus in overall urgency. Estimated mission costs currently approach $4.9 billion. Launch concepts place the departure window sometime in the mid-2030s. And beneath all the engineering language sits a remarkable shift in scientific posture. Humanity is no longer discussing whether it should search these oceans for life. The conversation has already advanced to designing the instruments that might recognize it when they arrive. The dry river valleys on Mars still remember the direction water once flowed. They cut across crater walls and ancient plains in branching patterns unmistakably shaped by liquid erosion. Some channels extend for thousands of kilometers, others empty into basins resembling long vanished lakes. From orbit, the landscape carries the geometry of a world that once behaved very differently from the frozen desert we see today. Early Mars was not the planet we know now. More than 3 billion years ago, the atmosphere was thicker and warmer, rich in carbon dioxide, and likely mixed with nitrogen gases that trapped heat near the surface through a greenhouse effect. A greenhouse effect occurs when atmospheric gases prevent heat from escaping efficiently into space, raising planetary temperatures. Under those conditions, rivers moved across the surface and lakes collected in deep impact basins. There may even have been an ocean. Several planetary models suggest a shallow northern sea once covered roughly 20% of Mars, stretching across low-lying terrain in the planet's northern hemisphere. Shoreline-like formations remain debated, but the evidence for large standing bodies of water continues growing stronger with each orbital survey. Mars also possessed another protection Earth still retains today. A global magnetic field surrounded the young planet, generated by motion inside its molten core. Magnetic fields deflect charged particles streaming outward from the sun, shielding atmospheres from gradual erosion. Earth's magnetosphere still performs this function continuously. Mars lost that shield long ago. Roughly 4 billion years ago, the Martian core began cooling and solidifying. As internal motion slowed, the magnetic dynamo weakened and eventually shut down completely. Without magnetic protection, solar wind began stripping the upper atmosphere directly into space. Solar wind is a constant stream of charged particles flowing outward from the sun at enormous speeds. The loss was relentless. Over hundreds of millions of years, Mars gradually surrendered most of its atmosphere and surface water. Lakes evaporated, rivers disappeared, temperatures collapsed. What remained froze underground or escaped into space entirely. NASA's MAVEN spacecraft has measured that escape directly since arriving at Mars in 2014. MAVEN, short for Mars Atmosphere and Volatile Evolution Mission, studies how gases continue leaking away from the planet even now. During periods of intense solar activity, atmospheric loss accelerates dramatically. But the central question in Mars science is no longer whether the planet was once habitable. The evidence for ancient habitability is overwhelming. What matters now is timing. Life on Earth appears astonishingly early in the geological record, emerging within roughly 700 million years after our planet formed. If biology develops readily when conditions stabilize, then ancient Mars may have possessed enough time for microbial ecosystems to originate before the environment deteriorated. And Mars preserved places where those conditions once existed. Inside Gale Crater, where NASA's Curiosity rover landed in 2012, scientists identified an ancient lake bed containing all the major chemical ingredients associated with life. Carbon was present, hydrogen, oxygen, nitrogen, phosphorus, sulfur. These elements existed together inside a stable, liquid water environment for extended periods. The planet may not have remained habitable forever, but for a time it appears to have been remarkably Earth-like. A single methane molecule survives only briefly on Mars. Ultraviolet radiation from the sun steadily tears the gas apart through photochemical reactions in the atmosphere. Photochemical means chemical change triggered by light energy. Under Martian conditions, methane should persist for only about 300 years before breaking down completely, which creates a problem immediately. If methane exists in the Martian atmosphere today, something must be replenishing it continuously. The gas cannot be ancient residue lingering from the planet's distant past. It has to be entering the atmosphere in relatively recent time, somewhere within the last few centuries at most. Methane itself is simple. One carbon atom bonded to four hydrogen atoms. On Earth, methane forms through two dominant pathways. Geological activity can generate it through volcanic heat, hydrothermal reactions, and chemical alteration inside rocks. Biology produces it as well, primarily through microorganisms called methanogens that metabolize hydrogen and carbon compounds in oxygen-poor environments. Mars appears to contain no active volcanoes today, which made the first detection deeply intriguing. In 2013, NASA's Curiosity rover identified trace methane inside the atmosphere of Gale Crater. The rover carries a tunable laser spectrometer, an instrument that identifies gases by measuring how molecules absorb specific wavelengths of light. Initial readings were extremely small, only a few parts per billion, but the concentrations refused to remain stable. Over subsequent years, Curiosity detected seasonal fluctuations in methane abundance. Levels rose during the Martian summer and declined again during winter. Seasonal behavior implied an active source responding to environmental change rather than random contamination or instrument error. Then came the spike. In June of 2019, Curiosity recorded the highest methane concentration ever measured on Mars, roughly 21 parts per billion. The increase appeared rapidly, almost overnight, then faded again within days. Scientists immediately conducted repeated follow-up measurements to verify the reading. The signal remained real, but another spacecraft complicated the mystery dramatically. The European Space Agency's Trace Gas Orbiter arrived at Mars in 2016, carrying atmospheric instruments roughly 100 times more sensitive than Curiosity's spectrometer. From orbit, it should have detected methane easily if the gas were globally distributed. It found almost nothing. Again and again, orbital observations failed to confirm the methane Curiosity measured from the surface. The contradiction remains unresolved. Somehow, methane appears locally near the ground while remaining nearly invisible at higher altitudes where atmospheric circulation should eventually mix it. No explanation fits comfortably. One possibility involves subsurface microbial ecosystems releasing methane through biological metabolism, with temperature changes controlling how the gas escapes through underground fractures during warmer seasons. Another explanation focuses on perchlorates, highly reactive salts common in Martian soil, chemically interacting with buried organic compounds to generate methane abiotically, meaning without life. But neither possibility is ordinary. Both scenarios require active subsurface chemistry still operating on Mars today. The planet would not be geologically and chemically dead after all. Something below the surface would still be reacting, changing, and releasing gas into the thin atmosphere above. Chris Webster of NASA's Jet Propulsion Laboratory, who leads Curiosity's methane investigations, described the readings with careful understatement. Quite startling, Jezero crater was chosen because something once flowed into it slowly. Long before Perseverance arrived, orbital imagery revealed a fan-shaped deposit spreading across the crater floor, the unmistakable outline of an ancient river delta preserved in stone. On Earth, river deltas are extraordinary biological archives. Fine sediments settle gently through calm water, burying organic material layer by layer before oxygen and radiation can destroy it. Over immense spans of time, those sediments harden into rock while preserving chemical traces of ancient environments. NASA aimed Perseverance directly at one. The rover landed inside Jezero crater on February 18, 2021, after descending through the Martian atmosphere, suspended beneath a supersonic parachute. The landing site was not selected simply because water existed there once. Many places on Mars show evidence of ancient water. Jezero was chosen because it may have preserved biosignatures, chemical or structural traces left behind by ancient life. That distinction matters. Previous Mars rovers focused primarily on habitability, asking whether conditions suitable for life once existed. Perseverance was designed for a sharper objective. It searches for evidence that biology itself may have once interacted with the Martian environment. Its instruments reflect that shift immediately. Mounted near the end of the rover's robotic arm is Sherlock, short for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. Sherlock uses ultraviolet Raman spectroscopy, a technique that identifies molecules by analyzing how light scatters when it strikes them. Different compounds scatter light differently, creating distinct spectral fingerprints. The instrument can map organic compounds at sub-millimeter scales. That level of precision allows scientists to examine exactly where molecules appear inside a rock, rather than merely confirming their presence broadly. Distribution patterns matter enormously because biological activity often organizes chemistry in ways random geology does not. Perseverance does not simply analyze rocks and move on. It drills cylindrical core samples directly from selected formations, seals them inside sterile titanium tubes, and stores them on the Martian surface for eventual retrieval. By 2024, the rover had collected 23 carefully selected samples from multiple geological environments across Jezero crater. Several came from rocks altered by ancient water. Aqueous alteration means minerals chemically transformed through prolonged interaction with liquid water. On Earth, those environments often preserve microbial traces exceptionally well because water deposits fine sediments and dissolved minerals together under stable conditions. Then Perseverance encountered Wildcat Ridge. The rock formation appeared as fine grained mudstone deposited within an ancient shallow lake environment billions of years ago. In 2022, rover instruments identified the most complex organic molecules ever detected on Mars within that rock. The compounds were embedded inside sulfate minerals, exactly the type of mineral matrix known on Earth for preserving ancient biosignatures across geological timescales. Sulfates act almost like natural vaults. They shield delicate compounds from oxidation, radiation, and chemical breakdown long after surrounding environments become hostile. Some of Earth's oldest microbial evidence survives inside similar mineral structures today. David Shuster of the University of California, Berkeley, a member of the Mars Sample Return Science team, described the collected material with a single word: treasure. Right now, small titanium tubes are resting quietly on the floor of Jezero crater. Dust moves across them. Temperatures swing violently between day and night. Thin winds pass over rocks untouched for billions of years. Inside those sealed cylinders are carefully drilled cores of Martian stone collected by Perseverance, each sample chosen because it may preserve chemical traces from an ancient habitable world. No extraterrestrial material has ever carried this level of expectation. Mars Sample Return is a joint mission between NASA and the European Space Agency designed to retrieve those cached samples and transport them back to Earth. The plan sounds straightforward at first, but it requires one of the most technically difficult chains of robotic operations ever attempted in planetary exploration. Several spacecraft must work together precisely. A sample retrieval lander would descend onto Mars carrying a small rocket known as the Mars Ascent Vehicle. Nearby, Perseverance itself may deliver the samples directly to the lander, though backup helicopters derived from the Ingenuity design are also part of the architecture. Once transferred, the tubes would be loaded into the ascent vehicle. Then something unprecedented happens. A rocket launches from another planet for the first time in human history. The ascent vehicle would carry the samples into Martian orbit, where an Earth return orbiter launched separately by the European Space Agency would intercept the container robotically and begin the long journey home through interplanetary space. Current timelines place the samples arriving on Earth no earlier than the mid-2030s. But the real significance begins after arrival. The scientific instruments available in Earth laboratories are vastly more sensitive than anything engineers can currently land on Mars. Some can detect isotopic variations at atomic scales. Others can identify molecular structures measured in billionths of a meter. Isotopes are atoms of the same element containing different numbers of neutrons, and biological processes often leave distinctive isotopic signatures behind. A rover cannot carry laboratories of that complexity. Earth can. Scientists would examine the samples inside a specially designed sample receiving facility constructed with extraordinary containment standards. The laboratory must prevent Earth organisms from contaminating the Martian material while simultaneously ensuring any possible Martian biology cannot escape into Earth's environment. That second precaution is not symbolic. It reflects a serious scientific acknowledgement that the consequences of returning extraterrestrial microorganisms remain unknown, even though most researchers consider harmful Martian biology unlikely. Uncertainty itself demands caution. NASA's Office of Planetary Protection has already developed detailed response procedures for positive biological detections, protocols never previously required for any returned extraterrestrial sample. The containment standards exceed even those used in Biosafety Level 4 laboratories, the facilities designed for Earth's most dangerous pathogens. And all of this infrastructure exists because of what may be inside those tubes. Not fossils necessarily, not visible organisms, perhaps only microscopic chemistry organized in ways geology alone cannot explain. Molecular asymmetries, isotopic patterns, organic structures preserved within ancient sediments, small signals. But if those signals indicate an independent origin of life beyond Earth, the implications extend far beyond planetary science. Mars sample return remains under budgetary and scheduling review, with projected costs between $8 and $11 billion. Yet few scientific endeavors have ever carried stakes remotely comparable to what those sealed samples might contain. Sunlight reaches Titan as a dim copper haze. From the surface, Saturn would appear enormous overhead, blurred behind a thick atmosphere saturated with nitrogen and hydrocarbon smog. Titan is Saturn's largest moon, larger even than the planet Mercury, and unlike nearly every other moon in the solar system, it possesses a dense atmosphere. At sea level, atmospheric pressure there is roughly 1.5 times stronger than Earth's, and liquids move across the surface constantly. Not water, never water. Titan's average surface temperature sits near minus 179 degrees Celsius, cold enough that water behaves like solid rock. Ice forms mountains. Frozen water composes the crust itself. But methane and ethane, hydrocarbons that exist as gases on Earth, remain liquid under Titan's conditions. So Titan has weather. Clouds gather in the atmosphere. Rain falls onto the surface. Rivers carve channels through valleys before emptying into lakes and seas scattered across the polar regions. The moon possesses a complete hydrological cycle: evaporation, condensation, precipitation, and surface flow, but every stage operates through hydrocarbons rather than water. The scale is immense. Krakenmeer, Titan's largest known sea, covers roughly 400,000 square kilometers, making it larger than Earth's Caspian Sea. Radar observations suggest depths approaching 300 meters in some regions. Coastlines extend for thousands of kilometers beneath orange atmospheric haze. Nothing else in the solar system resembles it. But Titan forces astrobiology into uncomfortable territory because it challenges assumptions deeper than temperature or distance from the Sunday. It raises the possibility that life may not require water at all. On Earth, water acts as the universal biological solvent. A solvent is a liquid capable of dissolving and transporting molecules so chemical reactions can occur efficiently. Every known terrestrial cell depends on liquid water internally. Proteins fold within it. DNA operates inside it. Cell membranes stabilize because of it. Titan offers a radically different solvent environment. In 2015, researchers at Cornell University proposed a theoretical structure called an azotosome, a membrane potentially capable of functioning inside liquid methane. The name combines nitrogen and liposome, reflecting its proposed role as a methane-compatible equivalent to Earth's cellular membranes. Cell membranes are essential because they separate internal chemistry from the external environment. On Earth, they form as lipid bilayers. thin, double layered structures stable in water. But water behaves very differently from methane chemically. Molecules that organize naturally in liquid water often collapse under Titan's cryogenic conditions. The Cornell model suggested certain nitrogen based compounds might instead self assemble into flexible, stable membranes inside liquid methane. No one has observed such structures in nature. The concept remains theoretical, but the chemistry underlying the proposal follows established physical principles and past peer review within the scientific community. Titan therefore occupies a strange category in astrobiology. It is not simply another potentially habitable ocean world. It may represent an entirely separate framework for habitability itself. And beneath the frozen crust, evidence still points toward a deep, subsurface liquid water ocean as well, meaning Titan could potentially host both conventional water based chemistry below and exotic methane based chemistry at the surface simultaneously. Flying on Titan is easier than flying on Earth. The atmosphere is thick, dense with nitrogen and hydrocarbon haze, while gravity remains weak at only about 1/7 of Earth's pull. Wings and rotors generate lift there with remarkable efficiency. A human wearing artificial wings could theoretically glide through Titan's skies using only muscle power. NASA decided to build an aircraft instead of a rover. In June of 2019, the agency selected Dragonfly as the next flagship mission in its New Frontiers program, a nuclear powered rotorcraft designed to move across Titan by flight rather than wheels. The mission represents a major shift in planetary exploration strategy. Previous surface missions generally crawled across terrain, slowly, limited by rocks, slopes, and distance. Dragonfly will leap over all of it. The spacecraft resembles a large dual quadcopter with 8 rotors extending outward from a central body carrying scientific instruments and a radioisotope power system. Radioisotope power converts heat released by decaying radioactive material into electricity, allowing operation far from sunlight where solar panels become ineffective. Dragonfly launches in 2028. After a 6-year journey through interplanetary space, it is expected to arrive at Titan in 2034. Once deployed into the atmosphere, the craft will begin flying between multiple landing sites across the moon's surface, covering distances in hours that conventional rovers might require years to traverse. Its primary destination is Selk Crater. The impact structure spans roughly 80 kilometers across and may preserve one of Titan's most important chemical environments. When the crater formed, the tremendous heat of the collision likely melted portions of Titan's frozen crust, generating temporary pools of liquid water that may have persisted for thousands of years before refreezing. That matters because Titan already possesses abundant organic material. Complex hydrocarbon compounds, called tholins, blanket much of the surface in dark, reddish deposits. Tholins form naturally when ultraviolet radiation interacts with methane and nitrogen in the atmosphere, creating increasingly sophisticated carbon based molecules that drift downward onto the terrain below. At Selk Crater, those organics may once have mixed directly with liquid water. Many scientists view that combination as one of the most promising pathways toward prebiotic chemistry, the network of reactions that can eventually produce molecules associated with life. Dragonfly carries instruments specifically designed to investigate whether such chemistry progressed further on Titan than previously understood. Its mass spectrometer will analyze surface material for amino acids, nucleotide bases, and other compounds connected to biological or pre-biological processes. Amino acids form proteins. Nucleotide bases form the structural foundation of genetic molecules like DNA and RNA. But Dragonfly studies more than chemistry alone. The mission will sample Titan's atmosphere during flight, measure seismic activity through onboard sensors, and probe subsurface composition using a gamma ray spectrometer capable of identifying buried materials beneath the surface. Over a planned operational lifetime of roughly 3.3 years, the rotorcraft is expected to travel approximately 175 kilometers across Titan, more ground than all previous planetary rovers combined. NASA states the mission objective with unusual clarity. Dragonfly exists to determine how far Titan's chemistry has progressed toward life, or whether life itself may already exist there. Venus crushes and burns everything that reaches its surface. Temperatures there average roughly 465 degrees Celsius, hot enough to melt lead. Atmospheric pressure is approximately 92 times stronger than Earth's at sea level. Thick clouds of sulfuric acid surround the planet continuously, reflecting sunlight so efficiently that Venus shines brighter in our sky than any star. Nothing about it appears biologically inviting, which is why the phosphine announcement in September of 2020 shocked so many scientists so deeply. A research team analyzing observations from the James Clerk Maxwell Telescope in Hawaii and the ALMA Observatory in Chile reported evidence for phosphine drifting within Venus's atmosphere. The molecule immediately attracted attention. Phosphine consists of one phosphorus atom bonded to three hydrogen atoms. On Earth, it is associated primarily with anaerobic ecosystems, environments lacking oxygen, where certain microorganisms produce phosphine through metabolic activity. Swamps generate it, marsh sediments generate it. Some animal digestive systems generate it. Industry can manufacture it artificially as well. But nature rarely produces it without biology involved. Researchers searched for alternative explanations on Venus immediately. Volcanic outgassing was considered, lightning chemistry, photochemical reactions driven by sunlight in the atmosphere. None of the known abiotic pathways appeared capable of generating phosphine in the quantities initially reported. The original estimate approached 20 parts per billion. That concentration would have been difficult to dismiss as random noise if confirmed independently, but confirmation became complicated almost immediately. Reanalysis of the observational data reduced the estimated abundance substantially. Some teams argued the signal might be closer to 1 part per billion. Others proposed the apparent detection resulted from calibration artifacts or processing assumptions within the data itself. The debate spread rapidly through planetary science, yet the signal refused to disappear entirely. Independent studies, published in 2021 and again in 2023, revisited the observations using alternative calibration methods and atmospheric models. Both analyses reported phosphine signatures remaining above the instrumental noise floor, meaning the signal still persisted beyond expected measurement uncertainty. No consensus emerged, but something important shifted during the controversy. Attention moved away from Venus's surface and upward into the cloud layers between roughly 48 and 60 kilometers altitude. Conditions there differ dramatically from the inferno below. Temperatures range from near freezing to around 90 degrees Celsius. Atmospheric pressure resembles Earth's surface conditions far more closely than the crushing environment beneath. The clouds became the real focus. Long before the phosphine debate, Carl Sagan and Harold Morowitz proposed in 1967 that Venusian cloud layers might represent the only potentially habitable region in the inner solar system outside Earth itself. They speculated that microscopic organisms could theoretically survive, suspended within atmospheric droplets, drifting continuously through temperate layers while avoiding the lethal surface below. At the time, the idea remained largely theoretical. Now it receives renewed scrutiny. The phosphine controversy remains unresolved because the signal sits precisely at the edge between detection and ambiguity. It is persistent enough to resist dismissal, yet uncertain enough to prevent definitive conclusions. Upcoming missions may finally clarify the issue. NASA's Davinci mission and the European Space Agency's Envision spacecraft are both expected to examine Venus and its atmosphere in unprecedented detail during the coming decade. And Venus continues hanging there in the evening sky, brilliant, toxic, and strangely difficult to stop questioning. Mars did not become uninhabitable everywhere at once. The surface changed first. Once the atmosphere thinned and the magnetic field disappeared, radiation from space began reaching the ground almost unfiltered. Ultraviolet light from the sun bombarded exposed soil continuously while cosmic radiation penetrated downward from interplanetary space. Over immense spans of time, the surface environment transformed into one of the harshest radiation zones in the solar system. The chemistry changed with it. Martian soil contains compounds called perchlorates, highly reactive oxidizing salts formed partly through radiation interacting with surface minerals. Oxidizing compounds aggressively break apart organic molecules, making long-term biological survival near the surface extremely difficult. Any exposed chemistry there is constantly degraded by radiation and oxidation together. But the damage has limits. Radiation weakens with depth. A few meters below the surface, the soil itself becomes shielding. At depths between roughly 5 and 10 meters, harmful radiation levels drop dramatically. Underground environments remain cold, but they are protected from ultraviolet destruction and much of the cosmic bombardment above, which shifts attention downward. In 2018, the European Space Agency announced one of the most debated findings in modern Mars science. The Marsis radar instrument aboard Mars Express detected an unusually bright reflective layer buried approximately 1.5 kilometers beneath the south polar ice cap. Radar reflections reveal hidden structure underground. Different materials reflect radio waves differently, depending on composition and density. The signal detected beneath the polar ice resembled reflections produced by liquid water trapped below thick ice sheets on Earth. Scientists proposed the feature might represent a subglacial lake, roughly 20 kilometers wide. The comparison immediately turned toward Antarctica. Lake Vostok lies beneath nearly 4 kilometers of Antarctic ice and has remained isolated for somewhere between 15 and 25 million years. Despite that isolation, researchers studying accreted ice above the lake have identified viable microbial life adapted to permanent darkness, immense pressure, and extreme cold. Mars suddenly seemed less sterile again. Subsequent analysis identified additional radar bright regions surrounding the original detection site, potentially indicating an interconnected system of buried lakes beneath the South Pole. Debate continues regarding whether the reflections truly represent liquid water or unusual mineral deposits. But several possible heat sources could maintain liquid conditions underground, even in Mars's frozen environment. One possibility involves geothermal heat rising slowly from the interior. Another involves radiogenic heating, thermal energy released naturally through radioactive decay inside subsurface rock. Perchlorate salts may contribute as well by lowering water's freezing point substantially, allowing brines to remain liquid at colder temperatures than pure water normally permits. Then, InSight added another layer. NASA's InSight lander operated on Mars between 2018 and 2022, carrying an ultra-sensitive seismometer designed to measure internal activity. During its mission, InSight detected more than 1,300 Marsquakes across the planet. Mars was still moving internally. That mattered because geological activity implies retained heat beneath the crust. Heat means energy gradients, subsurface circulation, and potentially liquid reservoirs hidden far below the frozen surface. The image of Mars as a completely dead planet became increasingly difficult to sustain. The surface may have collapsed into cold silence billions of years ago. But underground, the story may not have ended. Europa dominates most conversations about life around Jupiter. But Jupiter surrounds itself with several worlds that appear to hide liquid oceans beneath their frozen crusts, each shaped by different internal histories and different levels of geological activity. Together, they suggest that subsurface water near giant planets may not be unusual at all. Ganymede is the largest of them. The moon exceeds Mercury in size and remains the largest moon anywhere in the solar system. For centuries, it appeared as little more than a bright point beside Jupiter. Then spacecraft observations and telescope measurements began revealing something stranger beneath its ancient ice. In 2015, the Hubble Space Telescope confirmed strong evidence for a hidden saltwater ocean inside Ganymede. The discovery relied partly on auroras. Auroras form when charged particles interact with magnetic fields, producing glowing bands near a planet or moon's poles. Ganymede is unique among moons because it possesses its own internally generated magnetic field. As Jupiter's immense magnetic environment shifts around Ganymede, the moon's auroral bands oscillate visibly. But they oscillated less than expected. Hubble observations showed the movements were being dampened, as though another conductive layer beneath the surface was resisting changes in the magnetic environment. Scientists concluded the most plausible explanation involved a global saltwater ocean buried deep below the ice. Salt water conducts electricity efficiently. Models suggest that ocean may lie roughly 800 kilometers beneath the surface, trapped under an enormous shell of layered ice. That depth creates a major challenge. Unlike Europa, where fractures and plumes may expose interior chemistry more directly, Ganymede's ocean remains heavily insulated from the surface above. Yet, it still exists. Callisto presents another variation entirely. Jupiter's outermost large moon appears geologically ancient and comparatively inactive. Its surface, covered in impact craters, accumulated over billions of years. It lacks the dramatic fractures of Europa and the magnetic complexity of Ganymede. Still, magnetic measurements suggest an ocean there as well. Data from the Galileo spacecraft identified magnetic induction signatures around Callisto consistent with a conductive liquid layer beneath the crust. Magnetic induction occurs when changing magnetic fields generate electrical currents inside conductive materials. Saltwater oceans respond strongly to those changing fields, creating measurable effects spacecraft can detect remotely. If confirmed, even Callisto may conceal liquid water below. The European Space Agency is now sending a spacecraft specifically to study these worlds together. JUICE, short for Jupiter Icy Moons Explorer, launched in April of 2023 and is currently traveling toward the Jovian system. Its timeline stretches far into the next decade, beginning in 2031. JUICE will conduct detailed flybys of Europa, Ganymede, and Callisto before eventually entering orbit around Ganymede itself in 2034. No spacecraft has ever orbited a moon other than Earth's moon before. JUICE carries 10 scientific instruments, including radar sounders, magnetometers, spectrometers, and particle detectors designed to probe hidden oceans and internal structures beneath the ice. But the mission's broader importance lies in comparison. For the first time, scientists will examine multiple ocean worlds around the same planet simultaneously, comparing how heat, chemistry, magnetic fields, and geological activity shape habitability across entirely different environments hidden beneath the same giant sky. At first, the bright spots looked almost artificial. When NASA's Dawn spacecraft approached Ceres in early 2015, cameras began resolving two intensely reflective regions inside Akator crater, a large impact basin on the dwarf planet's surface. Against the surrounding dark terrain, the spots glowed with startling brightness, visible even from hundreds of thousands of kilometers away. Scientists did not expect Ceres to look active. The dwarf planet resides inside the asteroid belt between Mars and Jupiter, surrounded by rocky debris left over from the solar system's formation. At roughly 945 kilometers in diameter, Ceres is the largest object in that region, massive enough for gravity to pull it into a spherical shape and earn classification as a dwarf planet. But it was still assumed to be mostly inert. The bright regions challenged that assumption immediately. Initial speculation focused on exposed ice reflecting sunlight, yet measurements showed the material reflected too strongly, even for relatively clean water ice. Something else coated the crater floor. Dawn eventually identified the deposits as sodium carbonate. Sodium carbonate is a salt compound that commonly forms when mineral-rich water evaporates and leaves dissolved material behind. On Earth, similar deposits appear in dried lake beds and hydrothermal environments. The implication was difficult to ignore. Liquid brine from beneath Ceres's crust may have reached the surface recently enough to leave visible mineral residues behind. Then the evidence became stronger. In 2020, scientists analyzing data from Dawn's final low-altitude orbital phase concluded that Akator crater still hosts ongoing subsurface activity. Briny liquid appears to migrate upward through fractures created by the original impact event, slowly reaching the surface before sublimating into space. Sublimation means transitioning directly from solid or liquid into vapor without remaining stable on the surface for long. The source reservoir likely lies several kilometers underground. Researchers estimate the brine pocket may extend across several kilometers internally, maintained through a combination of residual impact heat and radiogenic heating within Ceres itself. Radiogenic heating occurs when, naturally, radioactive elements inside rock decay and release thermal energy gradually over immense periods. Ceres retained enough heat to stay chemically active. Organic compounds have also been identified across portions of the surface. These include aliphatic organics, carbon-based molecules structurally similar to compounds detected inside carbonaceous meteorites. Carbonaceous meteorites are ancient primitive rocks, rich in organic chemistry, dating back to the solar system's earliest history. Then another mineral appeared. Hydrohalite was detected inside the bright deposits at Akator crater. On Earth, hydrohalite remains stable only in the presence of liquid water under cold conditions. Its existence on Ceres strongly suggests liquid brines were active there within the last few million years, remarkably recent on geological timescales. Ceres therefore occupies an unusual category in the search for extraterrestrial habitability. It is not a large moon orbiting a giant planet. It possesses no tidal heating from massive gravitational interactions. It is instead a surviving remnant from the solar system's formation that somehow preserved internal warmth, liquid brines, and active chemistry billions of years after its birth. A small world, still changing quietly in the dark between planets. The map of potentially habitable places in the solar system keeps expanding outward, not gradually, suddenly. As of 2024, scientists have confirmed or strongly suspected subsurface liquid water oceans on at least 8 different worlds: Europa, Enceladus, Titan, Ganymede, Callisto, Ceres, Pluto, and Dione. Additional candidates continue appearing as spacecraft return more detailed measurements from the outer solar system. The pattern no longer looks accidental. Pluto became part of that conversation after NASA's New Horizons spacecraft flew past the dwarf planet in 2015. Before the mission, Pluto was widely imagined as a frozen relic, geologically inactive and chemically exhausted. Then, New Horizons transmitted images of Sputnik Planitia, a vast, smooth basin shaped like the western half of Pluto's famous heart feature. The terrain looked surprisingly young. Young surfaces in planetary science contain relatively few impact craters because geological activity renews them over time. Sputnik Planitia appeared smooth and dynamic rather than ancient and static. Models suggested the basin may remain stable because a subsurface ocean beneath the crust prevents the region from collapsing and fracturing under its own weight. Even Pluto may still hide liquid water below. Dione, another moon orbiting Saturn, presents quieter evidence. Measurements indicate magnetic induction signatures similar to those observed around Enceladus. Magnetic induction occurs when changing magnetic fields generate electrical currents inside conductive layers, such as salty oceans. Scientists suspect Dione may conceal liquid water beneath roughly 100 kilometers of ice. Then there is Triton. Neptune's largest moon orbits backward compared with Neptune's rotation, suggesting it was likely captured from the Kuiper belt long ago. Voyager 2 observed active geysers erupting from Triton's surface during its flyby in 1989, making Triton the only confirmed geologically active body in the outer solar system beyond Enceladus. That activity implies internal energy still exists there. Many planetary scientists now suspect Triton also contains a buried ocean beneath its frozen crust. The farther exploration extends into the solar system, the more often hidden water appears waiting underneath ice and rock. This represents a complete reversal of earlier assumptions. Before the Galileo mission reached Jupiter in the 1990s, Earth remained the only known body in the solar system confirmed to possess liquid water. Habitable environments seemed rare, fragile, and tightly restricted to narrow distances from the Sunday. Now the picture looks almost inverted. Subsurface oceans may contain more total liquid water than all of Earth's surface oceans combined, possibly by enormous margins. Europa alone is estimated to contain between 2 and 3 times the water volume of Earth's oceans, despite being smaller than our moon. And Europa may not even be unusual anymore. The discovery of tidal heating, radioactive decay, subsurface insulation, and salt-driven freezing point depression revealed multiple ways worlds can maintain liquid reservoirs far from sunlight. Water no longer depends entirely on surface temperature or Earth-like conditions, which changes the logic of the search itself. Liquid water was once treated as an extraordinary exception requiring delicate planetary balance. But after decades of exploration, the solar system increasingly suggests the opposite may be true. Hidden oceans could be one of its most common features. For most of modern scientific history, life was treated as fragile. Biology textbooks once described habitability using a narrow set of environmental assumptions: moderate temperatures, stable liquid water, access to sunlight, atmospheric protection. These conditions seemed so specific that the habitable universe appeared confined to a thin region surrounding stars similar to our Sunday. Then Earth itself began contradicting that picture. Organisms were discovered thriving in environments previously considered completely uninhabitable. They lived inside acidic hot springs, beneath Antarctic ice, within radioactive waste, and near deep ocean hydrothermal vents, where pressure and temperature would kill most known species instantly. Scientists gave them a collective name: extremophiles. The term refers to organisms adapted to physical or chemical extremes once believed incompatible with biology. Their discovery did not simply widen the definition of habitability, it dismantled many of the assumptions underlying it. Tardigrades became one of the most famous examples. These microscopic eight-legged animals rarely exceed half a millimeter in length, yet they tolerate conditions astonishingly hostile to complex life. Tardigrades survive the vacuum of space, radiation doses 1,000 times lethal to humans, temperatures ranging from near absolute zero to roughly 150 degrees Celsius, and complete dehydration lasting decades. They accomplish this through cryptobiosis. Cryptobiosis is a survival state in which metabolism effectively stops. During dehydration, tardigrades replace much of their cellular water with compounds including trehalose, a sugar that stabilizes internal structures and prevents destructive ice crystal formation. In that suspended condition, they endure environments that appear entirely lifeless. Other organisms push different boundaries. Deinococcus radiodurans, a remarkably resilient bacterium, survives radiation exposures approaching 1.5 million rads, roughly 3,000 times the lethal dose for humans. Radiation shreds its DNA into fragments, yet the organism reassembles the damaged genetic material within hours using highly efficient repair systems. Then there is Pyrolobus fumarii. This archaeon, discovered near hydrothermal vents on the ocean floor, cannot survive below 90 degrees Celsius. It thrives near 113 degrees, temperatures exceeding water's boiling point at standard atmospheric pressure. Under deep ocean pressures, however, water remains liquid and chemically active. Life adapted there naturally. Some discoveries challenged biology even more directly. In 2010, researchers studying a bacterium called G. phage, one in California's Mono Lake, proposed that the organism might substitute arsenic for phosphorus inside parts of its biochemistry. The claim was later heavily disputed and remains controversial, but it reopened serious scientific debate about whether all life, everywhere, must use the same elemental framework found on Earth. Even salt became less restrictive. Halophiles, organisms specialized for hypersaline environments, thrive in salt concentrations roughly 10 times greater than seawater. That adaptability immediately became relevant to the briny oceans suspected beneath Enceladus, Europa, and Ceres. The cumulative effect of extremophile research has been profound. Every new organism discovered surviving under extreme conditions weakens the argument that extraterrestrial environments are automatically too hostile for biology. Conditions once considered fatal increasingly look merely unfamiliar. And with each revision, more worlds remain on the list. A fragment of rock breaks free from Mars. It does not announce itself. It simply leaves, thrown outward by an ancient impact powerful enough to excavate deep crust and accelerate debris beyond the planet's gravitational grip. In the silence that follows, the fragment begins a journey measured not in days, but in thousands of years, drifting through interplanetary space. This is the starting point of panspermia, the hypothesis that life, or the molecular seeds of life, can move naturally between worlds. Carried by meteorites, comets, or microscopic dust grains, it suggests that biology might not begin separately on every planet. Instead, it may spread. The idea is no longer treated as speculation alone. It sits within mainstream astrobiology, examined through orbital dynamics, chemistry, and experimental biology. The solar system itself provides constant physical exchange. Each year, Earth is struck by roughly 500 meteorites, most from the asteroid belt, but some traced to lunar and Martian origins through isotopic fingerprints preserved inside their mineral structures. Those fingerprints matter. They confirm that material is routinely exchanged between planets, even across vast distances and time spans. Once ejected, some Martian rocks follow trajectories that intersect Earth's orbit within a few thousand years, sometimes less. In geological terms, that is almost immediate. Life, if dormant, could theoretically endure that interval. On Earth, certain organisms already demonstrate extreme persistence. Bacterial spores and cryptobiotic states, such as those observed in tardigrades, allow biological systems to shut down metabolism almost entirely. In that condition, survival across long exposure periods becomes physically plausible under the right shielding conditions. But panspermia does not rely only on living organisms. The Murchison meteorite, which fell in Australia in 1969, contained more than 90 distinct amino acids. Amino acids are organic molecules that form the building blocks of proteins in all known life. 19 of those detected in the meteorite are also used by terrestrial biology. Their presence confirmed that complex organic chemistry arises naturally in space without any biological system guiding it. This expands the definition of possibility. It suggests that space itself is chemically active in ways once attributed only to life. If Mars once hosted microbial ecosystems during its early warm period, then ejecta from that environment may have been transferred to Earth repeatedly over billions of years. The reverse process is also possible, with Earth material ejected during ancient impacts, dispersing outward into the inner solar system. Laboratory experiments support the mechanics behind this exchange. When bacterial spores are subjected to simulated impact pressures and acceleration forces, a fraction survive the process intact, not most, but enough to keep the hypothesis scientifically open. That shifts the question. If life exists elsewhere in the solar system, it may not represent independent origins on each world. Instead, it could represent a shared biological lineage distributed across multiple environments, slowly adapting after separation. In that framework, life is not isolated, it is moving. A silence stretches across interstellar space. Not an absence of physics, not an absence of possibility, but a lack of anything we can currently interpret as intentional signal, structured communication, or engineered pattern. This is the core tension behind the Fermi paradox. The question of why a universe so old and so large appears quiet when life should, statistically, be common. The traditional framing assumes a linear trajectory. Life emerges, evolves complexity, develops intelligence, then expands technologically until it becomes detectable across light years. Under that model, the sky should be filled with evidence of other minds. But the solar system tells a more restrained story. Across Europa, Enceladus, and other ocean worlds, we find environments that could support life for billions of years without ever exposing it to starlight. Thick ice shells isolate entire biospheres from space itself, sealing them beneath kilometers of pressure and darkness. In that context, intelligence is not inevitable. It may not even be likely. A hypothetical ecosystem on Europa's seafloor would experience no day and night cycle, no visible sky, no changing constellations, no external reference to anything beyond its ocean. Life there, if it exists, would evolve entirely within a closed chemical world, powered by hydrothermal vents and molecular gradients rather than sunlight. No signals would escape. No curiosity would extend upward. Only survival would matter. But this reframes what silence actually means. It suggests that the universe may not be empty of life. It may simply be filled with life that has no pathway to broadcast itself. Microbial ecosystems could persist in chemically stable environments for geological timescales, perfectly adapted, fully successful, and entirely isolated. Carl Sagan once estimated in the 1980s that the Milky Way might host millions of intelligent civilizations. That estimate assumed surface-based evolution, where life has access to light, atmosphere, and environmental variation that encourages complexity over time. But if most life begins and remains beneath ice or rock, the statistical model changes dramatically. Subsurface oceans remove almost every external driver that leads to technological development. No fire, no metallurgy, no astronomy, no atmospheric chemistry visible from the outside. Only internal energy sources and slow biochemical cycles operating in darkness. In that revised model, silence is not unexpected. It is structural. The solar system itself becomes a case study in this possibility. Multiple worlds show strong evidence for long-lived liquid oceans, yet none show obvious signs of surface intelligence. Not because life is absent, but because it may be confined to environments that do not interact with space at all. But this does not diminish life. It reclassifies it. Life becomes something that can exist, persist, and diversify without ever needing to announce itself. A hidden biosphere model of the cosmos suggests that biology may be widespread, while communication and visibility are rare outcomes rather than inevitable ones. From this perspective, the question shifts. Not where is everyone, but how many never had a reason to be seen at all. A single reading on a screen could rewrite reality. It might arrive as a spectral line in a dataset, a microscopic structure in a returned sample, or a chemical imbalance that refuses every known abiotic explanation. However it appears, confirmation of life beyond Earth would not feel immediate. It would begin as verification, repeated analysis, and controlled doubt. Then certainty would settle in. The scientific meaning of that moment depends entirely on one distinction: whether the detected life shares ancestry with Earth or whether it is independent. That separation defines everything that follows. If it is related, the implications are subtle but profound. Shared genetic code, identical amino acid chirality, and matching biochemical pathways would suggest a common origin. That could point to material exchange between worlds through meteorites, or in the less likely scenario, contamination carried unintentionally by spacecraft. In either case, life would no longer be confined to Earth alone, but connected through a shared biological thread. But if it is unrelated, the consequences expand dramatically. Different amino acids, alternative molecular structures, or a fundamentally distinct genetic system would indicate a separate origin of life. That would mean life did not emerge once in the solar system. It emerged at least twice, independently, under different conditions. Two origins, one system. That possibility shifts biology from rarity to recurrence. It suggests that when the right chemical environments exist, life does not merely appear, it repeats. In that scenario, the galaxy no longer contains a handful of exceptional worlds. It contains countless biological experiments unfolding across time and space, each shaped by local conditions but driven by the same underlying chemistry. Estimates of 100 to 400 billion star systems in the Milky Way suddenly gain a different weight. Even if only a small fraction host life, the total number of living worlds becomes vast beyond intuitive comprehension. Not speculative abundance, but statistical consequence. The philosophical implications extend outward slowly, then all at once. Humanity would no longer be the only example of life's outcome. It would be one instance among many. That shift does not diminish significance, but it dissolves exclusivity. The idea that life is a rare cosmic accident would weaken under the pressure of repetition. Instead, life would appear as a property of the universe itself, expressed whenever conditions allow. The societal response would not be uniform. Scientific communities would focus on classification, origin tracing, and biochemical comparison. Philosophical and cultural systems would confront something harder to integrate: the loss of singularity. Human exceptionalism, long embedded in history, language, and worldview, would have to adjust to a broader context. The universe would no longer feel centered around a single emergence of life, but populated by many. And beneath all of it, a quieter realization would remain that the question was never only about discovery, it was about scale. And scale, once expanded that far, does not shrink again. A spacecraft is never truly empty. Before it leaves Earth, it carries fragments of the world that built it. Microscopic life clings to metal surfaces, survives in hidden joints, and persists even after sterilization procedures designed to eliminate nearly everything. These organisms are not intentionally transported. They are simply difficult to fully remove. This creates a quiet, scientific tension. Every mission to another world becomes both exploration and unintentional transfer. To manage this, NASA applies planetary protection protocols, a set of rules designed to reduce biological contamination of environments that might support life. For destinations considered especially sensitive, known as special regions where liquid water could exist, spacecraft must meet strict limits of fewer than 300 microbial spores per square meter of surface area. Even so, perfection is impossible. Before launch, the Curiosity rover was estimated to still carry around 65 distinct bacterial species, despite clean room assembly and sterilization procedures. These organisms are not necessarily active, but their survival potential cannot be entirely eliminated under current engineering constraints. But contamination is not limited to Mars. In 2019, the Israeli Bereshit lunar lander crashed on the moon during an attempted landing. Later analysis suggested that thousands of dehydrated tardigrades, microscopic organisms capable of extreme survival states, may have been on board in a dormant condition at the time of impact. The moon is not considered biologically sensitive, but the event highlighted how easily life can be transferred unintentionally across space. The deeper concern emerges when considering worlds that actually could host life. If Earth organisms reach Mars, Europa, or Enceladus before we fully investigate those environments, distinguishing native life from contamination becomes increasingly complex. Once introduced, Earth biology could potentially persist in sheltered niches, especially where liquid water exists. That possibility introduces a temporal problem. The search for extraterrestrial life is not only about distance, it is also about timing. Some astrobiologists argue that Mars, after decades of robotic exploration, may already have regions where distinguishing indigenous biology from Earth contamination is no longer straightforward. The more missions arrive, the denser the biological footprint becomes. This is why sample return missions are designed with extreme containment in mind. The Mars sample return architecture includes a dedicated Earth receiving facility built to exceed even standard Level 4 biohazard containment standards. Its purpose is twofold. It must prevent Earth biology from contaminating Martian samples, and it must also prevent any potential Martian organisms from interacting with Earth's biosphere until they are fully understood. The system works in both directions. That design reflects a growing awareness in planetary science. Exploration is no longer a one-way interaction with empty environments. It is an encounter between a biologically active planet and potentially biologically active others. But uncertainty remains unavoidable. We are still learning where life can survive, how easily it spreads, and how long it can persist without detection. Each mission refines the rules while simultaneously testing them. And the central question quietly intensifies, not only where life might exist beyond Earth, but how carefully we must look before we alter what we are trying to find. A sequence of launches is already unfolding across deep space, not as isolated missions, but as a coordinated unfolding of exploration that spans decades, distances, and entirely different worlds. Each spacecraft carries a specific question, yet together they form a single investigation into whether life exists beyond Earth. In the year 2030, NASA's Europa Clipper begins its close flyby campaign of Jupiter's icy moon Europa. Over 49 separate passes, it will skim through plumes and magnetic fields, sampling material ejected from a hidden ocean beneath the ice. For the first time, Europa will be chemically examined at close range rather than from distant orbit. The following year, ESA's JUICE mission begins its Jupiter system survey. It will study Ganymede, Callisto, and Europa, tracing differences between three ocean worlds orbiting a single planet. By 2034, JUICE will enter orbit around Ganymede, becoming the first spacecraft ever to orbit a moon other than Earth's moon. That same year brings another arrival. NASA's Dragonfly rotorcraft lands on Titan, beginning surface exploration of a world where liquid methane flows across frozen terrain. It will move between sites, sampling chemistry shaped by an entirely different kind of climate system, where organic compounds behave under conditions far colder than Earth. Meanwhile, deeper in time, Mars sample return advances toward its mid-2030s delivery. The mission will bring Perseverance's cached rock cores back to Earth laboratories. These samples will be examined at molecular resolution, offering the most detailed search yet for ancient Martian biosignatures preserved in stone. Around the same period, the Enceladus Orbolander concept, if approved and funded, moves into development phases. It is designed to fly through Saturn's plumes and then land near active fractures, directly sampling material from a subsurface ocean that may already be interacting with rock. In parallel, NASA's Dragonfly mission prepares for a descent through Venus's atmosphere during the late 2030s. It will measure cloud layer chemistry in real time, probing a region once considered impossible for life, yet now chemically intriguing. Each mission approaches a different world, but all are aimed at the same underlying question. Could life exist there, or does it already? The convergence of these missions within a single decade is unlike anything in planetary science history. Never before have so many independent spacecraft been directed towards so many potential ocean worlds at once, each targeting environments capable of sustaining chemistry associated with life. This creates a rare scientific moment of overlap. If even one mission detects a confirmed biosignature, every other active or planned investigation will shift immediately in priority. Instruments will be recalibrated, targets will be reassessed. Exploration strategies will tighten around the first confirmed instance of life beyond Earth. But even without discovery, the accumulation of data will reshape understanding. Each flyby, landing, and sample analysis builds a shared map of habitability across the solar system. Not speculative anymore, measured. And as the timeline moves forward, the question itself becomes less distant. It begins arriving in real time. Time moves differently when measured in rock, not in days or years, but in layers of sediment, mineral shifts, and chemical traces preserved across billions of years. Earth formed approximately 4.5 billion years ago, a young world still cooling from violent accretion, its surface reshaped constantly by impacts and volcanic upheaval. And yet, within that chaos, something appeared. The oldest widely accepted microbial fossils, known as stromatolites, date back roughly 3.5 billion years and are found in ancient rock formations in Western Australia. These structures were built by microbial communities, slowly trapping sediment in layered growth patterns, creating living records of early biology. Even older evidence exists. Isotopic signatures from Greenland rocks, dated to around 3.7 billion years ago, suggest biological activity may have been present within 800 million years of Earth's formation. These chemical patterns hint at life emerging quickly, almost as soon as stable conditions allowed it. That speed is striking. It suggests that under the right environmental conditions, life may not be an improbable accident, but a recurring outcome of chemistry itself. But after that first emergence, Earth remained biologically simple for an almost incomprehensible span of time. For more than 3.5 billion years, life stayed microscopic. Single cells dominated oceans, adapted to changing chemistry, and persisted through planetary transformations without developing complex structure. Multicellular life arrived late. Only around 600 million years ago did organisms begin forming bodies composed of many cooperating cells. From that point, complexity accelerated, eventually producing ecosystems filled with animals, plants, and fungi. But even that transformation is recent in geological terms. Intelligence capable of technology and abstract thought emerged within the last 300,000 years. That represents roughly 0.007% of Earth's biological history. A brief flicker at the end of an immense microbial timeline. This compression of complexity reshapes expectations for other worlds. If life exists in subsurface oceans, like those on Europa or Enceladus, there is no inherent reason to assume it has progressed beyond microbial forms. The environmental stability of those oceans, combined with isolation beneath thick ice, may favor long periods of biological stasis rather than rapid diversification. Earth's history reinforces that possibility. 4 billion years of microbial dominance, followed by a relatively sudden emergence of complexity, suggests that simple life is not a transitional phase. It may be the default state of biology under most conditions. And that reframes the solar system's ocean worlds. They are not necessarily waiting to evolve into something more complex. They may already represent the most stable endpoint life reaches in environments cut off from external energy, variation, and ecological pressure. In that context, silence does not imply absence, it implies continuity. If life exists beneath the ice of distant moons, it may be ancient beyond imagination, persisting unchanged for billions of years, operating at a scale and speed far removed from surface life. What we are likely searching for is not intelligence or civilization, but the universe's most common expression of life: slow, submerged, and almost invisible to time. A single confirmation would not rewrite physics. No constants would change. No equations would break. Daily life on Earth would continue in its familiar rhythm: cities moving, oceans circulating, people waking under the same sky. But something far deeper than infrastructure would shift, something built into the way meaning itself is structured. It would begin with recognition that life is not unique. For most of recorded human history, cultures across the world placed humanity at the center of existence, as though the universe was arranged around a single conscious observer. That framing shaped language, philosophy, and belief systems long before science began questioning it. Then came successive displacements. The Copernican revolution revealed that Earth is not the center of the solar system. Darwin's theory of evolution showed that humanity is not separate from the rest of biology, but part of it. Each shift reduced the sense of centrality, each one expanding the scale of what we are embedded within. But a confirmed second origin of life would complete that sequence. It would remove Earth from the center of life itself. What remains after such a shift is not absence of meaning, it is expansion of context. A universe that contains more than one genesis of life becomes a system where biology is not an isolated event, but a recurring outcome of physical law expressed under the right conditions. Some thinkers describe this as liberation. In that view, the discovery would dissolve the long standing feeling of cosmic solitude. Humanity would no longer be the only known instance of awareness in a vast and silent universe. Instead, it would be one example among many, part of a broader pattern that extends beyond Earth. But not all interpretations move toward comfort. For some philosophical and cultural frameworks, especially those that place unique significance on human life, such a discovery would introduce deep disorientation, not from loss of meaning itself, but from the redistribution of meaning across a wider cosmic field that no longer centers on a single origin. There is no consensus on how this would resolve. No historical precedent exists for it. What remains consistent across scientific communities is something more subtle. The researchers closest to this question, those who design instruments for Europa, Enceladus, Mars, and Titan, do not speak of alien life as abstract possibility. They speak of it as something approaching, not certainty, not expectation, but proximity. That proximity carries a particular tone. It is not detached curiosity. It is anticipation shaped by years of incremental evidence, each mission tightening the range of unknowns, each data set narrowing the space in which life might still be absent. And within that gradual convergence, a quiet understanding forms that the discovery, if it comes, will not arrive as spectacle. It will arrive as data first, then verification, then realization, and only afterward, meaning. At the widest possible scale, the distinction between space and biology begins to blur into a single continuum. What once felt separate, chemistry and life, now appears connected through the same underlying processes that operate across galaxies. The view changes when we stop focusing on planets and instead trace the raw materials themselves. The elements that define living organisms on Earth are not rare. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur exist in vast quantities throughout the universe, scattered across interstellar space and embedded in planetary systems, forming around new stars. They were not created on Earth. They were forged in the cores of ancient stars, stars that lived fast and died violently long before the solar system existed. Their explosive deaths seeded space with the foundation of everything that would later become chemistry, geology, and eventually biology. Between those stars, in cold molecular clouds drifting through the galaxy, simple organic molecules form naturally. Amino acids, sugars, and nucleobases appear without biological input, shaped by radiation, dust grains, and time. Radio telescopes have detected these compounds across multiple regions of the Milky Way. The implication is straightforward, but profound. The building blocks of life are not confined to planets. Meteorites reinforce this pattern. The Murchison meteorite, which fell in Australia in 1969, contains over 14,000 distinct organic compounds, many of them structurally complex. These are not biological remnants, but evidence that prebiotic chemistry operates independently of life itself. Even water, the solvent essential to all known biology, is not rare. It is the third most abundant molecule in the universe, forming in stellar environments and spreading through comets, icy bodies, and interstellar dust. Taken together, these facts suggest a system that is chemically biased toward complexity. But early interpretations struggled with this idea. Fred Hoyle once compared spontaneous life formation to a tornado assembling a complete aircraft from scattered parts. That image captured the intuition that order is improbable without design. Modern chemistry paints a different picture. Life does not appear to assemble in a single leap. It builds through gradual transitions, where each stage is chemically favored. Molecules concentrate in wet and dry cycles, in hydrothermal environments, in icy interfaces where energy and matter repeatedly interact over millions of years. In this framework, the universe is not random in outcome, but structured in potential. It continuously produces environments where complexity can increase step by step without requiring a single improbable event. From this perspective, life is not an exception placed on top of physics. It is one of its possible expressions, emerging wherever the conditions allow chemistry to persist long enough to organize itself into something that can recognize its own existence. And across the vast scale of space, those conditions may be far more common than once believed. There is a strange stillness that exists before a discovery becomes real. It is not absence. It is anticipation stretched across decades of work, instruments, and waiting minds. Somewhere in that quiet span, the answer already exists in motion. The first human to confirm extraterrestrial life has almost certainly already been born. They may be studying chemistry, or coding data pipelines, or calibrating instruments that do not yet know their own significance. Nothing about their current life would reveal the role they will eventually play, but the machinery that will lead them there is already turning. Europa Clipper is already en route through deep space. JUICE is moving through the Jupiter system. Dragonfly is being assembled for a world it has never touched. And on Mars, sealed titanium tubes rest in silence, holding fragments of another planet's ancient environment. The search is no longer theoretical. It is operational. Across multiple agencies and continents, spacecraft are already performing the work that will define a new scientific boundary. Each mission is a narrow beam of attention directed toward worlds where chemistry may still be active beneath ice, rock, or cloud. But what makes this moment unusual is not only the technology, it is the scale of precision now available to us. This species, which once crossed oceans with wooden vessels and mapped continents by starlight, can now measure trace compounds in plumes erupting from a moon more than 1.3 billion kilometers away. A single phosphorus atom, a single molecular signature, can be isolated and studied as evidence. That shift is not just technical, it is cognitive. It reflects a mind that has extended its senses far beyond the limits of its biology. The motivation behind this effort is also difficult to reduce to simple curiosity. It has persisted across every culture and every era of recorded history. Different languages, different cosmologies, different assumptions about reality itself, yet the same question repeated beneath them all. Are we alone? The instruments now searching the solar system are not separate from that question. They are its most refined expression. They translate an ancient human intuition into measurable data, into spectra and signals and chemical fingerprints. But what changes everything is the direction of the search. For the first time, the question is no longer aimed only at the sky in abstraction. It is aimed at specific oceans, specific atmospheres, specific chemical environments that may already be active. And that means the answer, if it exists, is no longer distant in principle. It is approaching in time, somewhere ahead, in a laboratory that already exists in possibility. A result will appear on a screen. A signal will resolve into certainty. And at that moment, a question that has accompanied humanity since its earliest awareness of the night sky will stop being a question at all. There is a moment, just before sleep fully takes hold, when familiar things feel slightly unreal. The sky above has always been one of those constants, unchanged from generation to generation, holding its position above every human life that has ever existed. Yet, what we now know about what lies within that sky quietly changes its meaning. Saturn is there tonight, as it was thousands of years ago, for ancient observers tracing its slow movement across the stars. It appears as a steady yellow point, calm and distant, indistinguishable to the naked eye from countless other lights. But within that single point, an entirely different world is active. Enceladus, hidden from view, is venting plumes of water, ice, and organic molecules into space at this very moment. Material from a subsurface ocean is escaping into the vacuum, dispersing chemical traces across hundreds of thousands of kilometers. Jupiter shines even brighter. After Venus, it dominates the night sky with a presence that feels fixed and silent. Yet beneath the surface of its moon Europa, a global ocean larger than all of Earth's oceans combined is moving in perpetual darkness, shaped by forces we can now measure but not yet fully witness. What appears still is anything but. The solar system, seen from this perspective, stops being a collection of isolated worlds and becomes something more integrated. A network of active chemistry, circulating energy, and persistent liquid environments existing far from the warmth of the Sunday. Water is not rare here, it is widespread. Organic chemistry is not exceptional, it is routine. Geological activity does not belong only to Earth. It echoes across moons and dwarf planets, each one carrying its own internal dynamics beneath ice or rock. From a distance, none of this is visible. From within, it defines everything. The missions described throughout this journey are built to translate that hidden reality into something measurable. Each spacecraft is an extension of human perception, tuned to detect faint chemical signatures, subtle thermal changes, and microscopic traces of complexity that might otherwise go unnoticed. And somewhere in that expanding field of data, a threshold exists, a point where chemistry stops being inert and begins to resemble something more. When that moment arrives, it will not announce itself loudly. There will be no immediate spectacle, no visible shift in the sky, only a reading that does not fit, a pattern that refuses to collapse into known explanations, a signal that persists after every alternative is tested. It will be looked at once, then again, and in that repetition, understanding will begin to form. The sky above will remain unchanged. Saturn will still rise. Jupiter will still glow. But the meaning assigned to them will no longer be the same. Because what changes is never the universe itself. It is the mind that finally learns how to see it.